Chemistry students, it's day 68. It's Tuesday, June the 2nd. We're coming down to the wire here. Just this and one more assignment after this, and you're done with the class. So you'll have about 5 days to catch up on old assignments. Okay, we're continuing on with kind of a challenging topic, and it's really my wish to kind of get you exposed to this. I don't expect you to master this totally, but kind of get exposed to the strategy of solving these kinds of problems, stoichiometry problems, particularly solution stoichiometry, because they're really central to chemistry. And as long as once you learn the strategy that I'm teaching you and just practice it, they're not as hard as they seem. But I want to walk you through some of them and have you, of course, try them on your own. Okay, so let's go ahead. We're now on the, let's see, we're now on, well, we'll go ahead with number 1. And how many grams of CaCl2 are required to prepare 150 milliliters of 2 molar solution? Okay, so what are we trying to find? We're trying to find over here grams calcium chloride, because that's what it's asking. How many grams of this? Okay, so that's all you're looking for. You're looking for grams. There's no denominator on this, so we're going to end up with just grams of calcium chloride. Okay, and are required to prepare 150 milliliters of 2 molar solution. So what does 2 molar mean? It means 2 moles of the solute, which is calcium chloride, for every 1 liter of the solution. Again, the solution is calcium chloride plus the water. But writing calcium chloride plus H2O over and over, it just gets kind of tedious to do that. So we just write it as solution. Okay, but you always want unit of measure and some substance that's applying to. Okay, and this is really just a puzzle. You're trying to figure out how to get from moles of calcium chloride to grams of calcium chloride, and then you're trying to figure out how to get from liters of solution to nothing on the bottom. Nothing appears over there on the bottom. So again, you pick either one or the other and start off. I usually start with the numerator, the top. So we need to get from moles of calcium chloride to grams of calcium chloride. Anytime we're talking moles to grams, it's a molar mass conversion. Okay, so what we need to do is get our periodic table. Okay, and here's the periodic table, just appeared in front of your eyes. So it's 40.8 for calcium, and chlorine is 35.45, and you have 2 of those, CaCl2. So we're going to go ahead and multiply those and add them together. And what we get for that is 110.98. So 1 mole of CaCl2 equals 110.98 grams CaCl2. So that's our conversion. So what we need to do is line that up. We need grams of CaCl2 to appear and moles to cancel out. So we're going to put grams on the top. Okay, what we have is moles of CaCl2 canceling there, and you're left with grams on the top, which is what you want in your final answer. So we've taken care of the numerator. Now what we need to do is take care of the denominator. We need to get 1 liter of solution to go away, to just totally disappear. How does that happen? Well, we see that we have milliliters up here to work with. So again, this is like putting together pieces of a puzzle so that they fit. So we know that there's 1,000 milliliters for 1 liter. So what we're going to do is get liters to turn into milliliters. And here we see that liters cancels with liters here, and now we have milliliters of solution, and we can make that totally cancel out by putting this 150 milliliters, because it says milliliters, 150 milliliters of 2 molar solution, so it's referring to 150 milliliters of solution. So it is the same unit and the same substance. Okay, so milliliters of solution cancels there and there, and we have nothing left on the bottom then. So every unit on the bottom is canceled out. So nothing on the bottom, the only thing on the top is grams of CaCl2. So now we can go ahead and add those up, or multiply those rather. So 2 times 110.98 times 1 times 150 divided by 1,000 divided by 1 divided by 1. So we'll go ahead and do that. Okay, and for that I get 33.3. So again, the overall strategy for this is identify what you're trying to get to, how many grams of CaCl2, write that way over on the left. What are you starting with? 2 mole per liter, 2 moles of CaCl2 per liter of solution. You write that over on the left side, and then you build a bridge. Okay, the two things you had to work with was a molar mass conversion and this 150 milliliters of solution. All right, so it's a little bit of a puzzle, but a little bit of practice and you can become really good at these. All right, next up. How many grams of iron oxide are required to prepare 420 milliliters of 4 molar solution? By the way, these are the kind of problems that you don't have to be a high-level chemist to do these. I do these types of problems when I'm mixing solutions for a lab, and I have to know how much of a solute I have to put in order to make a certain volume of a certain concentration and molarity. So all chemistry teachers have to do these types of problems. So they're not just theoretical, nor are they very high-level problems. Okay, so let's go ahead and do that. So we want to know grams of iron 2 oxide. So that's going to be grams. Okay, and we're starting off with 4 molar solution. So over here, way over on the left, it's 4 moles. Okay, so 4 molar means 4 moles of your solute, FeO, for every 1 liter of your solution. Okay, again, we're going to use a molar mass conversion. I didn't leave myself a lot of space, so I'm going to do that up here. Grab the periodic table. Iron is 55.85, oxygen is 16. If you add those together, you get 71.85. Okay, so one of these goes on top. We need to get from moles to grams. So we need moles to cancel out, so the grams are going to go on the top. Moles cancels with moles. We end up with the units that we're trying to get in our final answer, and there it is. Now, just like the last problem, this is very, very much the same. You got to get this to disappear. First thing we do is turn it into milliliters. So for any substance, it doesn't matter what it is. There's 1 liter. In this case, we're interested in the solution for every 1,000 milliliters of solution. Okay, and we got liters canceling there and there. And now finally, we need to, let me be sure I gave myself enough room here. We need to get this to disappear. Well, we just so happens we have a 420 milliliters of solution, so that's the units we need to go away. So we're going to put 420 milliliters of solution. Cancel and cancel. So nothing is left on the bottom as far as units, so there's going to be nothing here. So now we multiply 4 times 71.85 times 1 times 420 divided by 1,000 divided by 1 divided by 1. And for that I get 120.7 grams of iron oxide are needed to make 420 milliliters of a 4 molar concentration solution. Okay, so that's molarity. Let's move on to molality. So let's go back to our notes from yesterday. Let's review what molality is. So molality is moles of solute, just like molarity was on the top, but on the bottom it's totally different. It's kilograms. It's the mass of the solvent. And the solvent's always going to be water in these problems, H2O. And we know a special relationship of that is that 1 liter of H2O, this is only true for water, converts to a mass of 1 kilogram of H2O. So again, if you go to the 7-Eleven and you buy a 1 liter bottle of water, it's 1 kilogram. That's its mass. All right, so we're going to remember this relationship. We'll need it in some of these problems. Okay, 3. What is the molality of 45 grams of NaCl dissolved in 200 milliliters of water? All right, so the question is, what is the molality? So that means over here, way over here on the left, we're looking for moles. Okay, we're looking for moles of NaCl per kilogram of water. And what do they start us off with? They start us off with 45 grams of NaCl. So we're going to start that off way over here. Okay, in this case, it's dissolved in 200 milliliters of water, and I see I'm going to need something in the denominator. I'm going to put the 200 milliliters in right away. All right, so I need to get from grams of NaCl to moles of NaCl. So that's going to be a molar mass conversion. And let's go ahead and do that. NaCl is 58.44. I happen to know that. We did that in an earlier problem, or a problem yesterday. So moles of NaCl, 1 mole of NaCl. Okay, so there's the molar mass conversion. So again, the strategy is let's work with either the numerator or the denominator first. And as you can see, I'm going to start working with the numerator first. So we need grams to cancel out and convert to moles. So grams of NaCl cancels and cancels there. We're left with moles of NaCl, which is what we want in our numerator in the final answer. So we're done with the numerator. We've taken care of that. Now we've got to get milliliters of water, which is a volume. It's an amount that takes up a certain amount of space, into a mass of water, kilograms. All right, so first thing we want to do is convert milliliters to liters. So there is. Okay, so milliliters cancels here and here. And now we have liters of H2O on the bottom, but we need it to be in kilograms. Well, we have that relationship we just talked about right here between mass and volume. It only applies to water. So that's going to be this. 1 liter of water will give you 1 kilogram of water for every 1 kilogram of water. It's a lot of conversions. It's a busy problem. So liters cancels with liters of water. The only thing we have left on the bottom is kilograms of water and moles of NaCl on the top. So we're going to multiply 45 times 1 times 1,000 times 1 divided by 1 divided by 1 divided by 58.44 divided by 200. And that gives us 3.8 moles of NaCl per kilogram, but the proper way to write that is molal, 3.8 molal, and that's with a small m. So 3.8 molal is that answer right there. Okay. I don't want this assignment to go on forever. This problem is similar to that one. Not sure what this is. I guess that was just a conversion I did. You don't need to do that. So let's move on down. You're not doing these by yourself. You're doing them together. So let's just kind of get through a couple more of these, and we'll call it a day on this. Maybe the other two we'll do tomorrow. I don't know. Probably have some other problems though. Okay. Now mass percent. What is the mass percent of 56.7 grams of SO2 dissolved in 845 grams of water? We come over here. Mass percent. It's right here. It's grams of solute, what's being dissolved, into divided by grams of solution, what's doing the dissolving. The grams are going to cancel out, so you'll just have a number, and then you multiply that by 100 and then put a percent sign. Don't use the percent sign on your calculator. That'll mess you up. Just do the math here, grams divided by grams times 100, and then put the percent sign on the end. So let's go ahead and do that. So this one's not too hard. So this is molar mass. Or percent, mass percent, I should say. Okay, it's the grams of the solute over the grams of the solution. I actually said that incorrectly. It's not grams of the solvent, it's grams of the solution. That means you got to add these two numbers together. You want the whole solution, not just the water. So you're going to add these two, then take this, divide it by that number, multiply by 100, and then put a percent sign on the end. And that gives us 6.3%. So by mass, 6.3% is SO2. What does this really mean, percent composition by mass? Let's take a water molecule. And let's just round the numbers. The hydrogens are mass of 1, and the oxygen's a mass of 16. All right, so that's a total for a mass of 18 for a water molecule. If you wanted to know the percent composition by element, then you could easily see that 2/3 of a water molecule is hydrogen, and only 1/3 is oxygen. Or, put it in percentage terms, 66% 66.6% is hydrogen, and 33.3% is oxygen. So most of the molecule, if you just broke it down by what the elements are, most of it is hydrogen. But if you do it by mass, 16 grams of the 18 grams in a water molecule are oxygen, and 2 grams out of the 18 grams are hydrogen. So when you do that by a percent, you'll find out that it's about 89% is oxygen and about 11% is hydrogen. So that's what percent composition by mass is telling you. All right. And let's do one more problem and call it a day. We're going to go down to a mole fraction problem. Let's go look at the sheet. What is a mole fraction? So a mole fraction, it's kind of like mass percent, except it's moles of one solute over moles of all the solutes and solvent. So it's kind of the same thing, except instead of working with grams, you're working with moles, and you don't multiply by 100%. It's just a fraction. It's used in a certain area of chemistry that I won't talk to you about right now. You'll learn it in AP. But it's pretty common in some certain areas of chemistry. So if you're wondering why do they have all these different types of measures of concentration, it's because they're used in different areas of chemistry. Some areas of chemistry, most areas of chemistry find molarity to be the one that they want to work with. But there's other areas that use these, and that's about all I'll say about it right now. Okay, what is the mole fraction of 1.2 moles of copper oxide in 67 moles of H2O? All right, so it's just very simply going to be, this is mole fraction. It's going to be 1.2, and then you're going to add that to the water. And all we do is do that little math problem. That'll be our answer. I could have made the problem more complicated by giving you the substances in grams, and then you'd have to convert to moles, but no point. I'm just trying to show you what this does. And for that we get 0.18. So even though it's called a mole fraction, it's expressed as a decimal. Seldom in chemistry do you use fractions. I'm trying to even think of where you would even use a fraction in chemistry. It really does not show up. I'm sure there's somewhere that I'm not thinking of off the top of my head. But anyway, it's called a mole fraction, but you express it as a decimal. And there's no percentage sign, nothing like that. Okay, we're at 20 minutes. I think that's enough. Again, we're just trying to get a feel for how to do these stoichiometry problems. I'll give you some more tomorrow, including one complicated one, just to show you kind of where you're going with this. Again, it's just developing a strategy and practice, and you'll get good. You don't have to be good at math to do these. You just have to kind of get good at seeing how to set these up. Okay, so give you your last assignment tomorrow, and I'll see you then.